Hello everyone and welcome to another scientific video, the 11th scientific video of TEP Proster Productions. And today in this video we are going to discuss how to calculate the distance from the Earth's surface to the Sun in a very easy way. First of all, I am making the same request from all of you. If you haven't subscribed to my channel, please do it, because this particular channel is going to be one of the largest scientific vlogging channels in very near future. And let's move on to today's video. How to calculate the distance to the Sun. Many people were asking from me, is it too difficult to calculate the distance to the Sun? Do we need advanced technologies? Do we need advanced telescopes? Do we need laser beam reflections to calculate the distance from the Earth's surface to the Sun? And my answer was always no, we don't want anything like that. We want only basic maths, basic applied maths to do this. And especially the knowledge of trigonometry. That's what we are going to use very simply to calculate the distance from the Earth's surface to the Sun. Okay. Let's say now this is the Earth. This is the Earth. And here I have drawn Sun as a small object. Normally the Sun is bigger than the Earth, but for now, just for the calculation, we have drawn like this. Okay. Now the Earth, the radius of the Earth is R. This one also R. This one also R. Distance from the Earth's surface to the Sun is D. Is taken as D. And here, let's say the Earth is rotating in this way, so that by 12 noon, we can see the Earth, we can see the Sun like this straight away up in the sky. How to find out the exact time of 12 noon? We can place a needle-like thing under sunlight, and we can check the time that the shadow of the needle-like thing disappears. The time at which the shadow of the needle-like thing disappears, that is the exact 12 noon. At that time, we have to check the okay. At that time, we can take the angle direction to the Sun as 0 degrees. Then, as the Earth rotates, what will happen? The observer is moving like this together with the Earth. Observer is moving like this together with the Earth. Then after a few hours, this observer can see the Sun like this. Can see the Sun like this. So that there's a certain angle. Let's take that angle as alpha. And during this time, as the Earth rotates, let's take the rotated angle of the Earth as alpha. Sorry, this one as theta. The angle at which we can observe the Sun as theta, and the rotated angle of the Earth as alpha. Okay, now we can draw a perpendicular line like this. So that this one is 90 degrees, this one is alpha, and this one is 90 minus alpha. So if it is 90 minus alpha, we can draw another perpendicular line like this. So that this 90 degrees, if this 90 minus alpha, this is going to be alpha. Right. This one is theta, this one is alpha, this one 90, this one alpha. And we can take this one as, this angle as beta. Now what will happen? Now this one is a triangle. So this angle plus this angle plus this angle is equal to 180 degrees. Now we can see this one is beta, this one is 90 degrees, this one is alpha, and what about this one? If this one is a perpendicular line, this is the radius of the Earth, and this is a perpendicular line drawn to this. So if this is alpha, this is gonna be this is theta, this is gonna be 90 minus theta. So this is beta, this 90, this alpha, this 90 minus theta, so that beta is equal to 180 degrees minus 90 degrees minus alpha minus 90 minus theta. Finally, after solving this one, we can get beta as theta minus alpha. Now we can take one trigonometrical expression like this. If this is R, this length is R sin theta. This length is L. L is equal to R sin theta. Then again, we can take another expression like this. If the distance from the Earth's if the distance from the Earth's surface to Sun is D, and the distance, this small distance is L. So This full length is d plus L. D plus L, right? If the distance, if d plus L, then this angle is beta. Then L is again equal to d plus L tan beta. D plus L tan beta. D plus L tan beta is equal to L again. Now we can make L equals L. L equals L. So R sin theta, R sin alpha is equal to d plus L tan beta. D plus L tan beta. Here we know that beta is equal to theta minus alpha. Theta minus alpha. So that we can apply this value instead of beta. We can do it later on. Okay, now what is this L? What is this small distance L? Small distance L. Another question. We can find it out like this. If this is R, this is also R because they both of them are radius of the earth. And this part can be taken as, if this angle is alpha, this part is equal to R cos alpha. R cos alpha. So that L, small distance, is becoming equal to R minus R cos alpha. R minus R cos alpha. It means R within brackets 1 minus cos alpha. 1 minus cos alpha. Now we can apply this particular value instead of L. So R sin alpha is equal to D plus R 1 minus cos alpha tan beta. Now we know that beta is equal to theta minus alpha. Theta minus alpha. So that we can apply this theta minus alpha instead of B. So finally we can take that R sin alpha is equal to D plus R 1 minus cos alpha multiplied by tan theta minus alpha. Tan theta minus alpha. Then we can take that tan theta minus alpha to this side and we can take R sin alpha divided by tan theta minus alpha is equal to D plus R 1 minus cos alpha. R sin theta, R sin alpha divided by tan theta minus alpha is equal to R plus D plus R 1 minus cos alpha. Finally, we can take D in one, we can keep D in one side because that is the one we want to calculate. The distance from the Earth's surface to Sun, that is the one we have to calculate. So that we can isolate this one, we can take all the things to one side. We can make the subject D. So that D is equal to R sin alpha divided by tan theta minus alpha minus R 1 minus cos alpha. This is the formula, this is the equation that we are going to use to calculate the distance from the Earth's surface to Sun in the next step by using numeric values of theta, alpha and R. And let's move on to that calculation part soon. Okay, now we are moving on to the calculation part. Here, this diagram, R is the radius of the Earth and D is the distance from the Earth's surface to the Sun. And this is the equation that we derived. D equals R sin alpha divided by tan theta minus alpha minus R 1 minus cos alpha. Now, what is alpha? Now we are going to calculate alpha. Alpha is the rotated angle within our measured time. Our selected time was 4 hours. We did the experiment within 4 hours. So that in 4 hours, 4 hours means 14,400 seconds. In a day, as we calculated, we have 85,512 seconds. So that what we have to do is to calculate alpha, 360 degrees divided by 85,512 seconds multiplied by 14,400 seconds. Finally, alpha is coming as 60.623070 degrees. Then we have to find out theta. Finding out theta, the angle which makes from the observer to the Sun at the second question is very crucial because you can see the radius of the Earth is very much smaller compared to the distance from the Earth to the Sun. So if you are not measuring accurately the theta value, our calculation is going to be vastly wrong. So that we have to use a very sensitive telescope, a magnifiable telescope, to accurately find the angle theta at least for 0.23 decimal points. Then we can do it again and again and again for about 4 times. Then we can take the average value of theta. Then we can take an accurate value for theta. So we did the experiment for 4 times and we obtain values. I will not mention all values here. Theta 1, theta 2, theta 4, theta 3 and theta 4. Then we took the average so that for our value, for our experiment, the value came as theta was 60.623227.856 degrees, the average value for this theta. Now, this means theta minus alpha is, here we have alpha, here we have theta, and theta minus alpha is 0.00202856 degrees. 0.00020856 degrees. Now we can apply these values in the equation of this here. D equals sine alpha means sine 60.623070 divided by tan theta minus alpha means tan 0.00020856 minus r 1 minus cos alpha means again this one. Alpha means again this one. 1 minus cos 60.62307. Okay. 60.623070. Okay. Now R, what is R? The radius of the in the sunrise method. In a previous video we calculated the Earth's radius using sunrise method, and the value is 6.396544 multiplied by 10 to the power 6 meters. That's the radius of the Earth. Now we can apply this R value to here and here. Finally, sine 60.623070 is 0.871470 divided by tan 0.00020856 means 3.671877 multiplied by 10 to the power minus 6. Then R minus cos alpha, or the cos 60.6230 means 1 minus 0.49044, because cos alpha is here, cos alpha is 0.49044. Finally, after calculating all these things by applying R value here, and here, is the final value that we can obtain is 1.5188 multiplied by 10 to the power minus 10 to the power 11 meters. 1.5188 multiplied by 10 to the power 11 meters means 151.88 multiplied by 10 to the power 6 kilometers, or 151.88 million kilometers. So the distance from the Earth's surface to Sun, we have accurately, successfully calculated using only trigonometry, the basic trigonometry and basic maths. The value obtained is 151.88 multiplied by 10 to the power 6 kilometers, or 151.88 million kilometers. Okay, this is the end of another scientific video. Thanks for watching. If you like the video, please like. If you like the channel, please subscribe, and see you again with another video to calculate the mass of the Sun. See you there soon. Thank you very much.